Hello and welcome to this example for Qi 3003. In this example today we're looking at a boiler. Now this boiler is being fed with methane and also with oxygen at 500 degrees Kelvin. This combusts and it leaves the boiler at 1000 degrees Kelvin, and what we're wanting to know is how much heat is generated by the boiler. In addition, we know that the feed rate to the boiler is 10 moles per second of methane. So in the feed we're told that this is a stoichiometric mixture of methane. So what that means is that for the combustion reaction for methane, we've just got, for every mole of methane we've got 2 moles of oxygen, and that goes on to form 1 mole of CO2 plus 2 moles of water as well. So for the 10 moles of feed of methane, we're expecting 20 moles of feed of oxygen. So I've started by looking at this problem, and of course we start by doing this by drawing the system. And so the system's pretty straightforward here. So I've got my inlet conditions, which is the methane and the oxygen coming in at 500 degrees Kelvin, and then I've got my outlet conditions, which is at 1000 degrees Kelvin, which is just CO2 and H2O. And so I've got heat leaving the system, which is what I'm interested in. And so to analyze this system, I've made a range of assumptions. So I've assumed that the system's at steady state. Okay, I'm not interested in the dynamic behavior of this system. I've assumed that all these gases are ideal gases. Now, that should be quite reasonable at a lowish pressure. Now, I have to have a look again to see if we're told what pressure this is at. So we're not told what pressure the boiler's operating at, but it wouldn't be operating at a very high pressure. So it's reasonable to assume that it's an ideal gas. The kinetic and the potential energy effects are negligible. That's perfectly reasonable compared with all the energy released by combustion. There's no work going on here, okay, so I'm not generating any work right now. The system's at constant volume. Now, the assumption that I haven't made yet is that the combustion is complete. Okay, so I need to make this assumption to be able to complete the mass balance for this system. So I start now by doing the mass balance. Okay, and I'm just going to make my life a little bit simpler here just by adding some notation. So instead of having to write CH4 and O2 and CO2 every time, so I'm just going to say that this is A plus 2B goes to C plus 2D. Okay, so this makes it a little bit easier just to keep track of what's going on. So with my mass balance table, I'm interested in what's coming in. Okay, so my initial flow of methane is 10. Now this is all in moles per second. My initial flow of oxygen is 20. My initial flow of carbon dioxide is 0, and my initial flow of water is also 0. It's just methane and oxygen coming in. Now my change. Okay, so what's happening inside my reactor? So all of my methane is combusting. All of my oxygen is being consumed in the combustion reaction. And so for every mole of methane I react, I produce a mole of carbon dioxide. And then for every mole of methane that's reacted, I produce 2 moles of water. So what this means then is at my exit, okay, I'm getting 0 moles of methane, 0 moles of oxygen, 10 moles of carbon dioxide, and 20 moles per second of water coming out. Okay, so I'm just going to call these NA, NB, NC, dots for all of them because they're rates, of course, and ND. Okay, so I'm just using the naught notation for the inlet, and then I'm just calling it NA, NB, and C for the outlet there. And so I've used these names here because you should be familiar by doing these sorts of balances through ICE tables, maybe in first year chemistry, and then also, of course, these are equivalent to the mass balances you will have done in process principles. So then moving on to my energy balance equation. Okay, so I'm doing my energy balance here. So now my assumptions are that I'm at steady state. Okay, I've also assumed that I'm not doing any work as well. So this then simplifies to 0 is equal to Q dot plus n dot in H in minus n dot out H out. Okay, so that's goes to, so I just bring the Q on the other side, and so that's equal to n dot out H out minus in H in. Okay, so now that we've got this equation, what our task is now is to find what these terms are here. Okay, and so to find these, then we break the inlet stream and the outlet stream into their components. So if we have a look at the inlet stream to start with, so my flow in times by the average enthalpy in is equal to the flow of A times by the enthalpy of A plus the flow of B times by the enthalpy of B. Okay, so we'll remember from up here that the enthalpy of C and D at the inlet is 0, so we don't need to include those. Then for the outlet, the flow out times by the average enthalpy out is equal to the flow of C times by the enthalpy of C plus the flow of D times by the enthalpy of D. Okay, again, if we go back and have a look at our mass balance table, then we see that the flow of A and B, so methane and oxygen, at the outlet 0, so I don't need to include those terms. So now the task becomes, okay, so I know the flows, I've already got them from the mass balance table. So now I need to give a reference point for my enthalpies. Okay, and so to do this, I'm going to say, okay, let's make the enthalpies relative to elements, elements in standard state at 298.15 Kelvin, where, okay, so the enthalpy is equal to 0. Okay, so for oxygen, in this particular case, as a gas at 298.15 Kelvin and at standard conditions, the enthalpy is 0. So we can calculate an enthalpy relative to that. And so for our enthalpies then, we can calculate them as the enthalpy of formation, okay, the standard enthalpy of formation at 298.15, plus the integral from 298.15 to whatever temperature we're interested in, Cp to T. Okay, so, and the important thing here is because we've assumed ideal gas conditions, then we can use the ideal gas heat capacity, which we know is just a function of temperature. Okay, so if I take an example here of doing this for component A, so I can say A as an example, so we'll look at the enthalpy of A as it comes in to the system, and I'm just going to write a very general equation here. So the heater formation at T1, okay, which we know is 298 Kelvin, plus the integral from T1 to T2. And so the CPs are in the form A plus BT plus C on T squared. Okay, so that's a very general form to T. And so then we can do the integration. So this is still just the heater formation at T1 plus the integral, so AT plus BT squared on 2 minus C on T. So between T1 and T2. Okay, so now just solving the integral, or subbing in the values for the integral, T1 plus A T2 plus B, okay, plus C outside of the inverse of T1 minus the, or sorry, the inverse of T2 minus the inverse of T1 in there, and that should be a minus sign before the C there, so we'll just put that in. Okay, so now we've got a general form of the equation, and so what I need now is to get the data together that I need to do that. So so to get this data, then I'm using the heats of formation and the data tables from Lee. These are similar to ones that you have access to in the problem sets, and so I'm just looking for the components that I'm interested in here. So so the first component we're going to come across is methane. Okay, so methane gas here. So we take this data, carbon dioxide gas, take this data as well. I'm just going to quickly jump down to oxygen. Okay, so we take the oxygen data, and of course we expect the heater formation for this element, okay, at its standard state, at its stable phase, to be 0, okay, and that's what it is for oxygen, of course. And now we go back to water, and I'm going to use the gas phase data for water. Okay, an important thing here is that you've actually got a choice between liquid phase data or gas phase data. Okay, so even though water's not a gas at 298 Kelvin and 1 atmosphere, we could still calculate that if it was an ideal gas at that temperature and pressure, this is the enthalpy of formation it would have. And the reason we choose this is simply because to do the calculations, this one's convenient. Okay, because it saves us from having to do the whole phase change thing in the calculation. So now that I've got all the data, I can go back to my problem and just stick all this into a table so I can do the calculation. So I'll put all this in, and we'll jump forward a little bit. Okay, so we've now got all the data together. So we've got the heater formation data for each of the components, and of course the heater formation is 0 for oxygen since it's an element at 298.15 Kelvin. We've got each of the components of the heat capacity equation for each of the components, and then over here the temperature we've identified is the temperature at the inlet for methane and oxygen, and the temperature at the outlet for carbon dioxide and for water. And so then for each of those components we've calculated the enthalpy at that temperature. And if we compare the enthalpies at the temperatures we're interested in with the enthalpies of formation, what we see is that the enthalpies are less negative, which is what we expect, because the inlet temperature of 400 Kelvin is higher than 298 Kelvin, and the outlet temperature of 1000 Kelvin is higher than 298 Kelvin. So the enthalpy should be more positive or less negative. So this immediately allows me to check that I haven't made a mistake somewhere in the calculation. So now that I've got all this data, I'm able to stick all this into the energy balance equation. Okay, so from earlier I'm able to say that the heat in is equal to the outlet flow, so 10 moles per second of carbon dioxide, times by the enthalpy of carbon dioxide, plus 20 moles per second of water, times by the enthalpy of water, okay, and then minus the flow in of methane, which is 10, times by the enthalpy of methane, minus 20 times the enthalpy of oxygen coming in. So if I add all those things together, what I get is negative 7383 kilojoules per second. Okay, so which is approximately equal to 7.4 megawatts. Okay, so now looking at this then, what I have is I have a negative here, which is what I expect. I expect heat to be leaving the system. And then I've got a number of the order of several megawatts, and that seems reasonable to me for a boiler. So I'm pretty happy after checking that these enthalpies have changed in the correct way compared to the heats of formation, seeing that this is negative and seeing that this is several megawatts. Okay, then I'm pretty happy that what I've got here is a reasonable solution. Okay, so that's all for that. Any questions about this, please post on Piazza. Okay, thanks, bye.